Hey everybody, today this video lesson we're going to talk about something called intermolecular forces. And then we're going to talk about one of the two types of intermolecular forces near the end of this video. Now let's begin by defining this vocabulary word, intermolecular forces. Inter meaning between, molecular referring to molecules, and forces. We're taking a look at attractions between molecules. There are two types of attractions that we're going to be talking about. I will list both of them now, but we're only going to be talking about the first one. They are London dispersion forces and dipole-dipole forces. Now, in terms of strength, intermolecular forces are considerably weaker than bonds. If we were to list the different attractive forces in chemistry in order from greatest to smallest, the highest would be the ionic bond. Ionic bonds are the strongest attraction. They are positive-negative attractions between oppositely charged particles. The next strongest is a covalent bond, and then finally an intermolecular force. So in the grand scheme of things, intermolecular forces are weaker than any bond. But these intermolecular forces play an incredibly important role in the world that we live in, which I hope to illustrate with you over the next few slides and video lessons. We are going to begin with the first of two intermolecular forces. This one's called a London dispersion force, sometimes just abbreviated LDF for short. I'm first going to explain to you what a London dispersion force is. I'm then going to talk about the different types of molecules that exhibit London dispersion forces. And finally, I'm going to explain to you how we know London dispersion forces actually exist. What evidence do we have in the observable world that London dispersion forces are a thing? First, what is a London dispersion force? We need to think about molecules on their microscopic level. If we were to shrink down the size of a molecule, what we would see are electrons, and the valence electrons specifically. And what they're doing is they're always moving. We draw Lewis dot structures as electrons in static place, but those bonds and dots are moving all around the valence energy levels of the elements. Sometimes the electrons are being shared between two elements, and we call that a covalent bond, but those electrons actually move out of the way, and two new electrons might come in. Electrons are not static, they're always moving. Now I'm going to draw a hydrogen molecule here, and I'm going to show the valence electrons being shared between the two hydrogens as equally, but I'm going to use kind of a highlighter tool here to represent kind of the bubble of the electrons, and this represents kind of an even sharing. It kind of looks like a peanut, where the electron clouds are equally dispersed among both hydrogens. Once in a while, the molecule has all the electrons kind of piled up on one side. Take, for example, this hydrogen molecule, H bonded to H. At any moment in time, hydrogen may have its electrons, due to random electron movement, all on this side. And for a moment in time, because all the electrons are kind of on this side of the hydrogen atom, we get a partially negative charge. It's not a full negative charge because there's not more electrons over here than over here, but partially negative. We use this symbol for partial negative, and that means if this side's partially negative, then the other side is partially positive. Now, if this is happening in two different hydrogen molecules at the same time, well then maybe the second hydrogen molecule has its electrons piled up on one side as well, and it has a partial negative and partial positive. And for a moment of time, the negative of one molecule is attracting the positive of another. Now, as soon as these electrons move, this attraction disappears. It just kind of vaporizes, evaporates into nothing. And these molecules no longer attract each other. But for a snapshot, a moment, this is why it's called an instantaneous attraction, because it happens and then it's gone. But the fact that it does happen is evidence in the fact that things like hydrogen, nitrogen, oxygen, these very small but nonpolar molecular substances have melting points. They will turn to liquid, and then the liquid will turn to solid. If you get the temperature cold enough, the attractive forces will cause these to attract, condense into liquid, and then freeze into a solid. So the fact that the molecules will change state of matter is in fact the evidence or the proof, which I was talking about here on the bottom. So we actually addressed what it is and also the proof that it exists. Now we need to talk about which type of molecules have LDF. And if a molecule has electrons, it's going to have London dispersion forces. So in summary, all molecules exhibit dispersion forces. Every single one, because they have to have electrons to be a molecule. They have to have bonds, they have to have dots, so all molecules exhibit dispersion forces. That's not true of the second intermolecular force we're going to talk about, but all molecules have London dispersion forces. Well, that takes care of this short video lesson. Thanks for watching.